Okay, everyone. Now let's have a look at a demo about the weibull probability plotting and also how to use the weibull probability plotting to model the data, failure time data under the temperature stress. So this demo is written in MATLAB. So let's first have a look at the problem. We have stressed failure data. Uh, they follow the Weibull distribution. And let's see, use the Weibull probability plotting to see whether the data follow the Weibull distribution. We have a random sample of a manufacturer's capacitor were tested to determine how temperature accelerated the failure times. So three temperatures were used: 85 Celsius, 105 Celsius, and 125 Celsius. A total of 40 capacitors operating at each temperature. So we have about 120 capacitors, 40 for this degree, 85 degree, and 40 for 105, and 40 for 125 degree. The readout times is 24, 72, 168, 300, 500, 750, 1000, 100, no, 1250, and 1500 hours. So at a particular time, I'm going to read among the 40 capacitors, how many of them failed? At 72, how many of them failed? 168, how many of them failed? Then all testing were completed in about 10 weeks. Okay. Now, the first step, we're going to look at the data. So this is a temperature. No, this is a time, readout time. Let me put it here. This is readout time. And this is failures. Readout failures at the readout times. Maybe the number of failures. So at 24, we found one failures. By 72, we don't have find any failures. 24 hours, we found one failure, two failure, and five failures under 125 Celsius. And then 72, I found zero more failures. And then one more failure, and then 10 more failures under 125 degrees. So those are the data we have. So this is a data set we have. So under now, how are we going to test whether the data follow Weibull distribution or not? So the first step we did is we calculate f. This is a lowercase f. This is the cumulative failures. That means at a particular time, at a particular temperature, how many failures we have. And in total, we have 40 capacitors in the beginning of the test. So at a particular time, and then we're going to do the cumulative at a particular readout time divided by 40. So we got the cumulative distribution. So those are the data. Now let's have a look at how Weibull probability works. So we just estimated f. We know that if the data follow a Weibull distribution, then ft equals to 1 minus exponential minus t over c power m. M is the shape parameter, c is the characteristic life. So this is a nonlinear equation. So what Weibull distribution, Weibull probability plotting did is the linear rectification. That means we're going to move f to this side, and then minus exponential to this side, and then we take log on both sides. So this will become log 1 minus ft, and then you have a minus sign here, minus log again, and then you take a log again, because you have a power 10. And then what we are going to get is this nonlinear equation will become this linear equation. So this part will become our y equals to a. This will become our x plus b. So m will become the slope, and the minus m log c becomes the intercept. So this is called linear rectification. So if the data follow the Weibull distribution, then if we convert f with this term and then we plot it against the versus the log t, it should follow a straight line. If it doesn't follow a straight line, then this is not Weibull distributed. So this is called Weibull probability plotting. Okay, and you see the acceleration. We have the physical acceleration of the stress, right? Using the stress condition. It only changes the characteristic life because characteristic life is accelerated. The shape parameter doesn't change. So if you have multiple stress data under different stress conditions, they should approximately follow the parallel lines with different intercept. So now this is our data. We have 3 different stress conditions. So if we do the Weibull probability plotting, so this cumulative f, and if we do the log minus log 1 minus f 85, so this will become our y. Now x is log t, as what we just discussed. X is log t, y is log minus log 1 minus ft. So in this side, this is y on the different stress condition, this is x. If we plot them, they should follow parallel lines, okay? Because if they don't follow the parallel lines, then I think either the linear acceleration doesn't work, or the data doesn't follow a Weibull distribution. Let's see whether the data follow the data follow the normal, follow the Weibull distribution, because at different stress condition you have a straight line. When you plot, let me put this right here. You see here, this is log minus log 1 minus ft, right? And this should be, I have this sign here. Why label is not right? Maybe I put this one. It will work. Let's see. Quit debugging. Let's do it again. Yeah, now we have the parenthesis log minus log 1 minus ft. Okay. Oh, I didn't put it in the right location. It should be here. Let's debug it again. This is a breakpoint. The program actually stopped at this breakpoint. You see here, this is x85 is red and circle. So red circle, this is 85. Approximate, this is not a straight line, but approximate straight line, right? And then x105 is a straight line, they are approximately parallel. So the data follows the Weibull distribution for under each condition. So we have logarithm of failure time, and this is our y. But at the same time, under each condition, I want to get the shape parameter, and I also want to get the characteristic life. You see here. And this is our response variable. If we put it right here, so this is a response variable. Now we have our x. Now I'm adding an intercept term. So originally I only have x. This is log t. Now I'm adding a column of 1 because I wanted the intercept. And also let's look at the y. We have all the y here, different y. They are estimated from. So this backslash y is the least square estimate of all the beta. Now we have 2 parameters. The first one is the slope. The first one is the slope. Second one is the intercept. So for each condition, we have two parameters. Now, the slope is just the shape parameters, because we see slope is just shape parameter. But the intercept is minus m log c, So characteristic like c is actually equals to exponential minus intercept divided by slope, because you take exponential, you have log. So what we did is we got M. We got M. This is a shape parameter. And we also got a C. And we continue to do that. Now we print them out. If we go to the command window, we see the temperature 85 degree, shape parameter is 0.57. Is this minus or? I think this is not minus. It's just the way I was trying to show the value. Maybe I use the semicolon, is much better in case it's confused with the negative sign. Okay, now let me save it and remove the breakpoints. Now let me run it again. Now this is a demo, weibull multiple stress probability plotting. We have three lines, and the data follows the weibull distribution under each stress condition, and they are parallel to each other. And then we estimated the shape parameter and also the characteristic life under each stress condition. And as we can see, M doesn't change much, right? M should be constant, but it's not strictly parallel, because M does change a little bit, because this is real data, we have uncertainty. But under 105 and 125 degree, M doesn't change much, but this characteristic life is under a linear acceleration. So this is a weibull probability plotting. Now, let me stop the recording.